Merci. So it began to be recorded.
Yes, thank you.
Are you okay?
Okay, then I'll start sharing. Do you see my screen?
Yes.
Yes.
Okay. Oh, I cannot relocate my screen. Okay, so let me go back. One. Doesn't work. I'm fighting a bit with my different screens at the moment. Just a sec. Well, you see the content of the talk. It will be about the biochar production.
Yes.
What we consider is very important is the quality of the biochar, because you see a lot of very different qualities of biochar on the market. They all look black, but they're not the same. Then the total co-production concept that we developed for both the biochar production and the bioenergy. I give a little bit of an environmental example, which we did. And then everybody who's close to the market always wants to know something about cost prices. And there we have some examples as well. I thought it would be nice to show you our combined knowledge, which over the years has been developed. And it is from also from 3 important EU projects. The first one was called FertiPlus. Then we had the Interreg project HortiBlues, which was also about substrates. And now we are in the Rustica for the biofertilizers. How to move on? No, exactly. I can with my screen. Yeah. So why the biochar plus bioenergy? And why do we think it's important eventually to move to large scale? Well, you can make biochar by pyrolysis, that is only heating the feedstock. The feedstock is the ingoing material, wood or straw, whatever you want to process. And you can also make it by gasification. Then you use a little bit of air or steam or CO2. And that is without burning everything. Otherwise, you would call it combustion. And at this elevated temperature, the biomass feedstock degasses, so a gas comes out. And this is a burnable gas. And from an environmental point of view, it would be really stupid not to use this energy source, because you can replace fossil fuels with it, and it prevents environmentally unfriendly gases to go to the atmosphere, because otherwise you would have hydrocarbons, methane, all sorts of environmentally unfriendly gases. So best is to burn it and use the heat or to make electricity out of it. So, and then from an economic point of view, it would be stupid as well not to use this gas, because it's an energy source and it adds to your revenue. So you can make a profit on it. So you have 2 products and they both have a positive value. So they add up to your profits in total. Then why the larger scale? At this moment, the production of biochar is too expensive. Of course, that depends on a lot of factors. For instance, the price of the material that you put in. If you would have your own material, people consider it maybe for free, but it does represent a value in the market. So if you have clean wood, it would easily go to 100 euros per ton. And if you consider all these costs, not only the cost of making it, but also of the wood that goes in, or the straw, or the whatever feedstock you have, then for most markets, it is really too expensive. And that includes, where we've done a lot of work, the replacement of peat in horticulture, where they are used to paying higher prices than most people which are operating in soil. So even for those applications, it would be quite costly. So you're looking for ways to reduce the costs. One way to reduce the price is by economy of scale. A good scalable technology is when twice the size is not twice the price. So that is economy of scale. You make it bigger, but it will cost a bit more, but not as much as doubling the size, doubling the price. So it would cost less. That is the economy of scale. So therefore, you have to look for a technology which is scalable to a substantial scale, because then the price per kilogram or per ton of biochar produced gets less. Larger scale also means that you have less heat losses, because a small installation loses a lot of heat. And very often people with smaller installations are already happy if they can make so much energy that they are self-sufficient. But we aim at making an installation which has a lot of excess energy, so energy to sell. That is both economic and environmentally profitable. So the right size of this bioenergy installation then depends on how much heat you can use, because heat is not so easy to transport. It's best to be at a location where you can use the heat. And there it depends then, of course, on how much heat they can use. And for many hours per year. And so how much megawatt hours at the location is then needed. For instance, for a greenhouse location, we aim at 50 megawatt thermal input. That would be like 20,000 tons of wood per year. And for instance, 4,500 hours of heat requirement. But for an industrial location, you can aim to a larger scale, for instance, 25 megawatt thermal input and 8,000 hours. That would be the year around. So day and night for 1 year. And then you would have to look at if there's also a local source of bioresidues, because if you have to transport them from very far, that might also be a cost and not to be environmentally too friendly. So then about the production technologies. I hope you can see this because it has a bit smaller letters. We tried 4 different technologies in the 12 years. So I'll try to get a pointer. Can you see my pen now? It's a little dot. This is aiming,
no
and this
problem.
is pointing now at the screw reactor, at the photograph. It's an Auger screw reactor, which has an input of 3 kilograms per hour. And we used it as our first installation. We still have it. We use it a lot because every time we have a new feedstock, and that could be like cocoa shells or straws or we tried even use substrates that came out of the greenhouse, came out of the pots, and then was made into biochar. So basically that was a lot of peat, to be honest, or coir in the UK. In England, they use cocoa fibers as a substrate, and then we turn that into biochar. So this is an installation we use a lot. It has a, on the top, which is not on the picture, you have a bunker, and then it's fed into this horizontal reactor. That is a screw, and it screws it very slowly over, say, half an hour to where you see a bucket here. And there it falls into a bucket, the biochar, and the gas is taken somewhere else. So this is externally heated. It's electrically heated. And that is not the way you would do it normally. Although from this type, you also have larger scale installations. For instance, the German Pirech reactor is very much like this. It's only slightly bigger scale, and they put it not completely horizontal, but otherwise it's fairly similar. And we can use here also different gases. We can use steam, we can use air, we can use CO2, because we have all these facilities in the lab. Then we also used a moving bed gasifier, and which is the drawing on the right. In yellow, you see here like a funnel, where again, on the left side, you have a bunker. You screw the biomass feedstock in, it falls into this funnel. And it is gasified, and while you all the time you bring material on the top, it slowly moves down as it material at the bottom is screwed out. So the biochar is in this case screwed out at the bottom, and the biomass is fed at the top. This we have at slightly bigger scale, 10 kilograms per hour, but it's very difficult to get this completely right. It depends on the porosity between the particles. It depends on 2 screw feeds. It really is a bit more difficult to get this right. It's not undoable, but it's slightly more difficult. Then we tried a bubbling fluidized bed. We tried this at the lab scale and the pilot scale. And there you feed the biomass into a sand bed. So that's a moving, it's kept in motion by air or by nitrogen. It's kept in motion, and therefore it reacts like a fluid. And the heat exchange is from the sand particles of the bed material on the biomass, and then there is no flames, but it will, by the heat, slowly degas and react. And what we found, the nice thing was that if the biochar degases, it becomes so light that it comes floating on top. And we thought this should be possible to make this into a very nice larger scale installation. But when we moved up in scale to 30 kilograms per hour, then it turned out it was not so easy, because then you have all sorts of variations in the fluidized bed, and the floating on top was not so common as we had hoped. So there you see that sometimes you have to move up in scale to find the new levels of problems when you scale up. That's what every engineer does. You go steps of 10 in scale, a factor 10, and then you find new problems and you solve them, and you decide every time, is it still a good idea? Is this technology still a good idea? So then we had to decide that this was not a good idea. And we tried a fourth technology, and that was gasification on a grate. And a grate is just steps. It goes down in steps. And there is a grate. It means that some air or some other gases can be provided under the frame. And then it has some steps usually which move, and then it moves slowly down a few steps. So this is a very common combustion technology, but it's usually not used for gasification. But the whole hardware is fairly conventional. Only we used gases in different amounts. We used gases in different places. And I'll show you a little bit about this technology, because we still think this is a good technology for further scaling up. And this is what we would like to take to a demo, going to 3 megawatts or 5 megawatts thermal input. And then maybe after that go for 25 or 30. So it can be scaled up to a large scale, and it will have economy of scale. It will get per kilogram or per ton of biochar, it will get cheaper if you make it larger. So the bottom line of this research, it says 10 years, in the meantime it's 12 years. You can make a good biochar with all these technologies, using gasification and operating it with the attention for the quality of the biochar. You really have to know how to do it. But once you know how to do it, the technology is not the limiting factor. You can make a good biochar with all these technologies. So something about the quality of the biochar. We always performed our experiments in such a way that we first asked the client, which was very often someone in a project, what is the particle size that you would like to have? Because we prepare the biomass in the particle size that the client wants to have. So if you want to replace peat in substrate, you want a certain, and you want to mix in other compounds, you want a certain pore size, sorry, a certain particle size. And therefore, that is what we do. We first make the biomass into the good particle size, and then we make biochar, and you don't have to do anything anymore, only water it. It is lightweight if you make it really degas, make all the gas volatilize out of the particles, then it is only 100 to say 150 kilograms per cubic meter. So think about sand at 1600 kilograms per cubic meter. This is very lightweight. And you see the pictures. It has, depending on the feedstock which you start with, it has a very high internal porosity, and that can hold water. It's not like peat swellable. It doesn't open up. It doesn't shrink if it's dry and open up if it takes up water. It's rigid. And it doesn't move anymore, but the pore sizes that are there, you can fill with water. And therefore, in some mixtures, in some dry areas, also in soil, the water holding capacity is important. For some applications it is, for others it isn't. Then we also, in an early stage, said we want to comply with the very best quality of biochar there is. And we found that the European Biochar Certificate, they developed a quality standard, and we want to fit with their supreme quality. Then that is the EBC, the European Biochar Certificate. There are some norms, for instance, the carbon, the hydrogen, and the oxygen just are criteria that are in place. So to make sure that you have degassed the particles all to a certain extent. And that also means that you probably have lost all your tar components. So the sum of the 16 EPA-PAH, polyaromatic hydrocarbon, is a sum of what we call in normal language tars, but if you are more in the business, you call it polyaromatic hydrocarbons. That could be carcinogenic to people. They're not doing anything bad for the plants, because by now it has been shown that if the levels are not too high, plants and bacteria can deal with it, and it will eventually disappear from the soil. But it's the people that have to work with it which have to be protected. And so there are regulations, and the EBC, the European Biochar Certificate, took a norm from the Americans, from the EPA, that made a sum of the 60 most dangerous ones or more common ones, and this sum has to be below a certain level. And the EBC has a criterion that says it has to stay below 12 milligrams of these tars on 1 kilogram of biochar, so that's very little. But the premium quality is smaller than 4 milligrams per kilogram of biochar. And these days we manage certainly the premium quality, and sometimes we're even under 1 milligram per kilogram of biochar. Then there are also criteria on the heavy metal concentrations. But there, I think the best message to send out is that these nearly always, or they are always coming from the feedstock. So if your feedstock is polluted, they will concentrate because there's gases going out, but the metals usually stay in the biochar, in the solid, and therefore it will accumulate and it might get over the threshold. So like every ingredient that goes to food or to soil, there is limitations for these metals, and it's best to keep in mind analyze for them in the feedstock, because they are in the feedstock. They're not dosed anywhere else, and that's the only source that is available. Then there is PCBs and dioxins and furans that have to be under a certain limit. But to be honest, maybe if you use plastics or something, but I've never seen any biochar that has been over the limit. Never. Not even detectable. And then these days, the European Biochar certificate also says that you have to use at least 70% of the heat in order to get some certification of being a good process. That, in our case, is absolutely no problem. So our TNO biochars, they all match the quality to the very best qualities. But we really paid attention. That is what I want to say. We always made this our main criterion if we were doing a good job or not, the quality. Then this is to just show you, maybe it's a bit difficult graph, how we evolved in the very early stages of our very earliest project, the 30+. We started off with what people asked from us, and that was pyrolysis. And that is here the very 1, 2, 3, 4, 5 bars that you see. And what you see, the colors, they are the different tars, and they are added up. And the different tars, in this case, they are the polyaromatic. If you are aromatic, you have one ring, a ring of carbons. And so they are grouped in 2 rings, 3 rings, 4 rings, 5 rings, and 6 rings. They have different colors, doesn't matter, because in the end, you sum them up. And that is what it says here on the left axis. In milligram per kilogram. And there you see that we very often didn't stay under this 14 milligrams per kilogram as people asked for us. And then we decided, why don't we try, because we had some experience, why don't we try gasification? And here you now see the very large indicator of all the gasification biochars that we did in 30+. And now you see some bars that are even bigger, but there are also a lot of bars that hardly come off the horizontal axis and are well below 1 milligram per kilogram. And the very high bars, they are the cyclones. So it's the gas cleaning. And in this gas cleaning, you have a cyclone. And in this cyclone, you basically have all the small particles that went with the gas, the carbon particles that were with the gas, and where the tars condensate on. And there you see, this is the stuff that you never want to buy as biochar. It's full of pollutants. So even though this is mostly carbon, and it looks black, it will probably smell awful like tars, and it is because it is full of tars which condensated on the very small amount of black particles, the carbon particles that were taken along with the gas. And this is the case all the time. These are all cyclone, all the large bars are all cyclone ashes. So this is just put in as a warning. Not everything black, not everything carbon is eventually a good product. It's not a biochar. This should not be called a biochar. This is waste, and this is dangerous waste. So now back to our concept. So we have this great gasifier now, which I put in simply as a picture of how they normally use biomass combustion. And you bring in some bioresidues, whatever they are put on the grate. Then over, say, half an hour, they move down the grate and they send a lot of gas. And the gas is burned here by bringing in some extra air in what we call the freeboard, that's the empty zone. And then it goes, the path goes past heat exchangers, which is a very conventional way of making steam. And from the steam, you can use the heat or make electricity. That's the energy part. And then, of course, you have to clean the gas. And then you have eventually the chimney. And there you can also use the CO2 that comes out in the greenhouse, which we have chosen. We have done a nice project where we proven that you can use this in the greenhouse to grow sweet peppers, paprika. So you make heat and electricity, but then at the bottom part here, in this case, biochar comes out, which is a bit coarse in this case. It's from pine. And you can either use this as peat replacement in potting soil, or like in the rustica, we use this as an ingredient in the biofertilizer. And eventually, either you can go from the potting soil, store it in the carbon in soil, or as a biofertilizer, also the carbon goes into the soil, and it should be addressed as carbon storage. And I think this is one of the very important things for the future, that you can go carbon negative, really carbon negative, taking carbon out of the sky, taking CO2 out of the whole process by using biomass, making energy from that, but also storing the biochar in soil. So in Rustica then, we use this pilot, and we make biochar as one of the building blocks in the biofertilizer. Why would it be a good idea to have biochar in a biofertilizer? Because I think it is known to reduce the leaching of the fertilizer compounds. So if you are somewhere in soil, you have a leek or lettuce or in the field, and you want to have your fertilizer close to your plants, you don't want to leach it out when you have a lot of rain and down goes your fertilizer to the groundwater level, and it's not in the place where the plants are. So to keep it at the spot where the plants are, it is a bit of a sorbent, so some might not be released as quickly as in a normal leachable fertilizer, but then it will stay in the area where the plant roots are. It can also improve the soil structure because it contains some air, and it has some water holding capacity. For areas where your pH is a bit acidic, it might raise the pH. And it will raise the soil carbon content. And when it's very stable, and we always make it at a temperature where it's very stable, it is a good form of carbon sequestration. And then it will stay over 100 years at least in soil. And some carbons have been found to stay more than 1,000 years in soil. So that is really a way of carbon sequestration, of making sure that your carbon is very, very stable for a very long time. What it doesn't do is bring available nitrogen. All the nitrogen in the biomass that was there before you made it into biochar has either been fixed in the structure, so in the carbon structure, or it is gone to the gas phase. So there's no nitrogen fertilizer in the biochar. So it has to come from something else. And that is where the other ingredients come in. So we have some insect frass or some digestion residues that are high in nitrogen, and they are mixed with the biochar to the correct carbon to nitrogen ratio, or whatever you want. And also it is mixed with compost in our case. When you use biochar, it gives off the potassium, the kalium, fairly quickly, and the calcium and phosphorus very slowly. So it is a bit of an uneven ingredient. And the quantity, the volume of potassium is very dependent on the feedstock. So if your feedstock is high in potassium, then your biochar will also be high in potassium. And it will be given off fairly quickly. So we have also advised some of the highly fertigated feedstock. For instance, we tried the stems and the leaves from the sweet paprika to make biochar of that. But they had been fertigated so enormously that they had a very high potassium level that we thought you have to dilute it. So you mix it with another source, which is not so high in potassium, because otherwise it's simply too salty. Your plants will be given such a high dose. It's like if they were given seawater, so much salt. So that's not so nice for plants, I understand. So you better make sure that if you have something very high in potassium, you mix it with something that is not so high in potassium. And then there's a lot of evidence in all literature, thousands and thousands of papers that show that biochar is best used together with compost. And you can mix it afterwards, but even better would be if you mix in biochar in the compost making, because then you reduce also some environmentally unfriendly gases. So you reduce, for instance, methane production, or you reduce some hydrocarbons that come from compost as well, the smelly compost. And also you absorb more of the nitrates, so NO3. And therefore, there is quite a large body of evidence that biochar and compost are a very good match. So this is a bit more in detail how our pilot looks like. It's a vertical column. That is the yellow that's also lined with bricks, so it can have a lot of high temperatures. And you can consider this as a vertical section through the commercial plant. So even though this grade section here at the bottom is only 1 square meter, which is very, very small for a grade, you have to understand that we can call it the pilot because it takes all these other things into consideration that are present in a commercial plant. So you have the grade here at the bottom. Then you produce not only the biochar, which you harvest at the bottom, but you also make this burnable gas, which we then burn here in the middle section. And the heat, this is a T, generated will here be, it says cooler in Dutch. It will be, by this heat exchanges, be exchanged into energy production. So this is about 30 kilograms per hour input, but that's basically limited by the small grade. That is why it's a huge installation. It is 3 stories high, so I think more than 10 meters high, 1 meter diameter, and it's a bit of a funny shape, but that is because we wanted to have all processes, so the burning and the turning into biochar, the gas production, and also the energy generation. And we have a patent on this process because by the way we divide the gases, how we use the gases, and also how we make use of the radiation heat by the burning of this gas. And I heard somebody doing also tar cracking. You could also just use just partially gas burning here and crack the gases and then take the gas out, which is basically our next phase in the development, to see if we can do more with the gas and just not burn it completely here, but just burn it partially, the part that is necessary for the heat, and then take the gas without the tars into the next phase. But this is the very conventional way of how people use biomass combustion, and that is why we think this could be the very easiest way to bring it to the market, because there's no tars anymore, not in the biochar, and they're all into the gas, but you burn them in the gas. So everything that can be burned will be burned and just go to CO2 and water in the gas phase. Okay, there's my cursor. So these are some pictures of the pilot. You see the bunker, and I'm not sure if you can see my cursor. So this is the bunker. This is a view from the top. And then at the bottom of this bunker is a screw where it takes it screws the biomass into the reactor. This is the bottom of the reactor. Here you see the drivers for the steps. So that's for the machining of the steps. And this is at the bottom where the biochar comes out, and it's taken also by a screw up into two vessels, which can change. If the one is full, you just change to the other. So we have to operate this installation continuously. If we do a test run, we usually work from Sunday evening to Friday lunch, 24/7. We have two set of crews that work both 12 hours, and the analyst also. Then this is the middle level, the second floor. And here you see one of the injections for air, where we burn the gas. And then this is the top of the reactor, of the top floor. And here you just see the bolts of the where the heat exchanger is hanging here in the top of the reactor. And then the gas is taken somewhere else to be further cleaned. And it goes via an afterburner just to make sure, but we never have to use the afterburner before it can go to the outside. And it goes through a filter for the cleaning. So something on the environmental issue. Maybe you all know, but I had no idea. Soil is the largest storage for carbon in the world. So this is a very nice picture. It comes from the Hortiblues project. I used it there, but it comes from the US. It doesn't say from where. That's a mistake. But if you look at for instance, the trees, you see the photosynthesis, which over the years have gone up by human emissions. And here the human emissions don't seem to be too large. And part of it is compensated by more photosynthesis, and part of it is compensated by going into the ocean. But still, what is remaining is causing our climate change. So it's not negligible. It is very important. But if you look at these numbers, then you see, if you compare it to the soil carbon, that is the organic matter in soil, that it's a huge number. And if we could make more soil carbon stay in soil, then we could compensate for some of the human emissions until we are able to reduce those and maybe reduce the climate change effect. So even though also the microbial respiration is large, look at this number of 2,300 of the soil carbon. That is huge compared to all the other emissions in the system. So when the biochar is very stable and we can add it to the soil carbon, it can last there for hundreds of years or even thousands of years. And the higher temperature you use for the biochar making, the more stable it is, the longer it will stay in this pool of soil carbon. Doesn't it do anything? Yes, it does. There's some consensus in literature, although still being researched, that after 100 years, roughly 30% is oxidized, but that is the easy degradable part, where the microbes can still use a bit of that, and they help to convert to CO2. But roughly 70% is after 100 years still in carbon, still carbon in soil, and therefore it is a very good way of carbon storage. And if you can use it as a soil improver, for instance, mixed with compost, it serves two goals. So it can serve as a biofertilizer ingredient or mixed with compost as a soil improver. At the same time, if you make your carbon very stable, it will also stay in soil as a carbon sequestration option. And we've done some life cycle assessment on this. It's by my former colleague Lydia, who's now working in France. She's working at the Uni La Salle, and she also, for Istica, she gave a presentation, I think, at some biochar conferences. I'm not completely sure, Celine, where that was.
Yes, it was in Rennes.
Yeah, she's in Rennes. And we still have contact because we were very good colleagues and also friends. So we worked on this together. The basis of this LCA work, the life cycle assessment, is that we have a reference process, which is basically 1 megajoule of fossil heat from coal, from natural gas, from whatever. And that we compare this to 1 megajoule of heat produced by biomass, but then also producing biochar and using the biochar as a peat replacement in soil. And this paper, I will not explain it in much more detail, but it showed that you can go carbon negative by using this replacement in peat, where you can leave the peat in place. It's a very good CO2 absorbent peat in the soil, and it should not oxidize and release the CO2 again. This is in our climate the very best option we have. So leave it in place, don't use it, and then find another material, which could be partially biochar, say 30 to 40% you can use for the peat replacement, and then use other ingredients as well. And if you afterwards bring it to soil and use it for carbon sequestration, you really go carbon negative. But that requires also this last step of bringing it to soil. My cursor. Now, a bit on the cost price, which is from HortiBlue's webinar. Well, this is a lot of assumptions, which I'm not going to do all with you, but it takes a certain fuel, it takes a certain size of the installation, it assumes a certain percentage going to biochar and the rest to energy. It also has to assume prices for the wood, which in this case was taken at 100 euros per ton. Then the investment, we consider this 15 megawatt thermal to cost approximately 10 million euros, with some extra for the biochar treatment, depreciation 12 years, the interest of 5%, and in the end you can also have your internal rate of return, which we would call profit, and we put that at 15%. 1.5. And we put some money in for the heat, which we can sell, and we assumed, which is not little, a biochar value of 350 euros per ton. But then you have to think that this is an aim. It only works if you go to commercial scale. Because I think I've sort of done the calculations many times. If you go for a very small installation and you are honest about what the price of the incoming biomass would be, then I think you easily get to 1,000 euros per ton. So this is what we aim for, and then we calculated a few cases. And this is it all depends on your system. So it's just to give you a few examples. So this is the normal combustion. And what you see is I added the costs and the benefits. So if your costs are higher than your benefits, you make a loss. That's not a good case. So if you would have no subsidy and you would like to have 15% for your internal rate of return, say your profit, then you would make a loss, and there you would not invest. And this is why I think everywhere biomass combustion for just producing heat has a subsidy on it, and it has to compensate the lack of benefits. So it compensates the high costs. And here I stacked the biomass price, which you see in green is very large. That is for the 100 euros per ton of wood. You see the variable cost, that is the cost of operation, and the capital cost over the, I don't remember, was it 10 or 12 years? And all the benefits are from heat. Now, if you look at biochar without any subsidy, then your revenues would be the heat and the biochar. But still, if you would have any subsidy, then at the current situation, you would still have a loss. The loss would be a bit less, but you still have a loss. Well, at least you would not have your 15% internal rate of return. If you would go, for instance, to a very cheap material, and here we've taken the wood that you can sieve out of compost, and you would put this at, I think we put it at 30 euros per ton at the gate. Then your price goes for the biomass goes a lot less. We've taken a bit of extra variable cost for the processing and for the drying. We've taken a bit of extra cost for the capital cost because you maybe have to do some filtering or sieving or whatever. But you see that this biomass price is very dominant. And if your revenues stay the same, you still not make a 15% internal rate of return, but I think you already make a profit. And then if you would do this with using waste heat for the drying, I think you're nearly there. So this is to show, but this is for 8,000 hours of heat use. And that is necessary to make this profit, the benefits, the yellow column in heat. That's another case. So what if we would have revenues for the carbon? I think everywhere in the world, we're going to pricing in CO2. So this is, this is with the subsidy. This is a Dutch subsidy that is in the darker green, the middle green, I would say. And the rest is the same. And then you have you store the CO2 from the chimney. And this is still a fairly low price. This is of a few years ago. At the moment in Holland, this already goes at 80. And I think the next coming years, it will go up quite substantially. For the US, I've already heard by 28, they expect 200 euros per ton for the CO2 in the USA. So this is going to be a factor of importance. And so if you can, this is avoided because but it represents money. It's the ETS system where you can ask, where you can trade if you have been granted this emissions. You can trade your emissions for a certain amount of money. And there you can see that with the subsidy, you make even more than a 15% internal rate of return. It was aimed at being, even. And this is the combustion case. With the biochar, you can do better. You can make more profit. And with the compost, even better. The compost residue, the wood residue. And if you dry it with residual heat, so really low temperature heat. So first you make energy, and the energy that is left from that, you can still dry your material. And that is even more beneficial. And then I think this is even closer to going to the future. This is an interpretation where we have no subsidy, but we get carbon credits for bringing biochar to the field. Because why would you only give credits for CO2, for avoided CO2 that comes out of a chimney? or CO2 which is captured from the chimney and put in an empty oil field or stored somewhere deep, because your biochar is carbon storage as well. And if we, and that is now at a voluntary scheme in some countries, but I think it could be legislation, it could be by law, that you get money for this type of carbon storage. And if you would put it at the same price as the ETS system, so the CO2 price from the chimney, in this case, I just put it at 50, you can see where this is going, because your heat prices will still be important. The biochar price is important, but then you have two revenues of the CO2, and this is just your conventional combustion system, which even if you take all your CO2 from the chimney, this is what they often call the BECS, so the bioenergy with carbon capture system, it would still not be, you would not get your 15% internal rate of return. This is getting much closer. I think it would be above zero. But if you look at these two, they are really very profitable. And I think these two carbon compounds, they get bigger and bigger, and they get more and more important. But you see, the price of the biochar will always be important, and the heat you also always have to use. So you have to go to a system where bioenergy and biochar are combined, and where you make best use also of your carbon credits. They will become important. So in conclusion, how to move forward? I think it's important to make a strong case for the carbon credits for the biochar storage in soil. And when you choose a location where you would like to have your biochar installation, choose a location where you have tradable CO2 credits, the ETS system. It's likely that it has to be fairly large to be profitable. That makes the business case better because of economy of scale. You need a location where they have a heat demand, at least for 4,000 to 5,000 hours per year, but better even day and night, the whole year round, 8,000 hours. And you see what the effect is of the price of the feedstock. So if you could find a feedstock which is a residue other than clean wood, so we never considered trees to be chopped down for wood. So it would always be a tree is chopped down, and then you make planks or whatever for construction, and what is left over is still residue, will be used for the biochar. But if it's cheaper, all the better. So I think if you would construct a biomass installation now, I think the risks, at least in Holland, for co-production with biochar are less risks for the future, because you take these carbon credits and carbon sequestration into account, which is very likely to become more important in the future. And then even if the technology choice we made, you have a fallback option that you could still make 100% bioenergy. Because if you want, you can use more oxygen and make 100% bioenergy. So that is a fallback option where we think investors would find that important, because then you can say that the installation will have only a small additional price compared to normal biomass installation. And the risk of this just small extra investment is, of course, very important, that this risk is fairly small compared to investing in something that would just be a biochar installation. So with that, I would like to thank you and ask you for some questions.
So thank you, Finn. Is there any question? Romain?
Yes. I have a free question, please. Thank you for the. I prefer to write the question to good understanding. Is possible?
Yes.
The first question is a specific process. Commentaire. I wrote in. In the size shapes input the process. I have the question. What size?
Romain, tu veux savoir quelle est la taille?
What size of the chips in the input of the process in TNO? The granulometry?
Yeah, that is in one of the first things I said is we always ask the client what size of biochar they want, because then we make the wood the same size. So if you want to use it for say peat replacement, we go for something like 5 to 8 millimeters. So there's more work in making a good biomass feedstock, but then you don't have any work afterwards.
Okay. Is the size input to control the size output?
Yeah.
Okay. And a second question is the quality of biochar. Have you studied the specific surface as a function of time and heat?
Yeah.
What you result, please?
I didn't completely. I understood yet that you said the BET, so the surface, the internal surface is a function of temperature and residence time. It is, yeah. So we often make the biochar. If nobody asks for something specific, we could make it at 400 degrees. We can make it at 850 degrees. But if people do not know, then we usually make it at 600, 650 degrees. And then we have, for wood, we have typical internal porosity of surface of 250 to 400 square meters per gram, which is pretty good, I think. But it depends a bit on the also on the feedstock, because if you have say part of the trunk of a tree, there you have these large channels which have to move the fluid from the roots to the leaves, and so these channels are so wide that you can free them up all, but then you don't go higher than 250 square meters per gram, because we don't make extra pores. We just free up the structure of the plant. So if you look at the structure of a piece of wood under the scanning electron microscope, and you look at the picture of our biochar, it almost looks the same.
Okay. And I have another question is, you say use biochar with compost. It's better. So I read the against. If you mix biochar and compost, you j'ai pas le mot en anglais, dégradé.
What do you degrade?
Degrade. You degrade.
Decrease the nutrients availability.
Yes.
Yes, availability is something that is related to time. So if you want to have a quick release of, for instance, phosphorus, part of the phosphor will be stored in the biochar, and they will only be available over longer periods of time. That is true. Yeah.
Okay. And the last, I have just a remark. You say carbon credit review, 80 euros by ton. The slide you explain the carbon credit revenue. So the carbon credit revenue depend on a life cycle analysis of your biomass. It's not
We don't hear
fixed.
you.
It's not fixed value.
That I didn't understand.
You understand?
Mm.
You say the carbon credit review is 80 euros by ton.
Yeah, it is.
Yeah,
It is not fixed. I know.
It's a false. It's just a price market. Ah là là, l'expliquer en anglais, ça c'est compliqué. Si tu peux m'aider, Céline, je veux juste dire que c'est le prix du marché financier. Et c'est pas lié au marché.
It's determined by the market.
Yeah, yes.
Yeah.
It's not. So
It's like the stock exchange. Eh? One day it's high, next day it's low. Yeah.
No, so the price of carbon depend on life cycle analysis of biomass. If you use oak or vineyard or agricultural waste, you have a different price.
Yeah. In the paper we didn't consider it, but we've done afterwards. We've done also. Sorry. How many years you need to let a tree grow back? Is that what you mean?
No.
Oh. Well, I think part of the CO2 prices, the carbon prices, they are also dependent on the legislation of the country. And the 80 euros per ton that I used is because the Dutch government has given a guarantee to the oil company Shell, well known, which also from the gas stations, that if they capture CO2 from their chimneys and they bring it to an oil field, they get a guarantee from the Dutch government that they will get 80 euros per ton. So part they get from the ETS system, which is different every day. But for instance, if the ETS only gives them 50 euros per ton, then the Dutch government will pay 30. And that is to take away the risk from the companies, because if they find it too risky, they will not invest. So there's different governments dealing in different ways with how to promote and what to stimulate.
Okay, I think it's an international price because I think SBTi flag to determine and control the price.
Yeah, I think for people investing, some security and price is very often very important, because then they have a view of what they will get in the next 20 years and they know how they can earn back their investment. I think some form of price fixture could help people making investments. Yeah.
Okay, thank you.
Is there any other question?
Yes, hello. We are here to represent a gardening agricultural system, and we just wanted to know if how many times can we add biochar in our soil before reach the saturation, and what scale of time? I don't know.
Oh, saturation. That is something I don't know. I think you would have to ask an agronomist. But I think people find it at this moment way too expensive. Mm-hmm. So there are, I think, publications where they used a big bulk of biochar in compost in one go and then monitored it over, say, the next 6 years. But there's also a lot of experiments where people use, say, 10% biochar in compost. And then they bring it on every year to be able to afford it, to be able to pay the price. Okay. So I don't think anyone has tried what would be the maximum, because I think people consider it not realistic because of the price.
Yes. just another question. You said that biochar is known to reduce the leaching, but if biochar capture fertilizers, there is a risk of capture and release fertilizers compounds in the soil after a scale of time.
Is there a risk? I don't understand the risk.
Capture and release of fertilizer and compound in the soil.
But if you bring on fertilizer, I think the idea is that you will release it and the plants can use it, right?
Yes, but in the water after a certain time, can we found a molecule of something due to add of biochar?
Something that were in the biochar which are not supposed to be there, like heavy metals or so.
Yes.
But that depends on the quality with what you start. So if you, for instance, you would not have clean wood, but you would have painted wood, for instance, from demolition of houses or whatever, and in the paints are, in the old paints there is, for instance, lead, then you will get this in the biochar, but that should never go to agriculture or to soil. So that is why they put in the limits for the heavy metals.
Yes.
So it's a matter of also checking on quality. I don't think biochar can be used without some sort of quality control.
Mm-hmm. Yes. And biochar cannot capture some fertilizers molecule or something.
Yeah, it can. So there is the positive interpretation that you say it captures fertilizer elements and then it will release them more slowly.
Yes.
If you do the same interpretation negatively, you would say it captures the fertilizer elements and then it's not available in the short time.
You say that the phosphorus is released quite, it takes a long time to release phosphorus and it's more quick for potassium. Yeah.
Yeah. I think, but that is also beyond my expertise. But what I read in the literature is that people think that you would need fungi, so, such as mycorrhiza, to release the phosphorus, and then they live in symbiosis with the plant, and then the fungi, the mycorrhiza, they make the phosphorus available for the plants, and the plants make photosynthesis, and then they exchange in soil. Well, they both benefit. So, but then it takes a bit of time for the fungi to release the phosphorus.
Okay. Thank you.
Thank you.
Not sure if there's more questions.
On a perdu Céline?
I don't see Celine anymore.
Yeah, exactly. With the boss. Thank you very much for your presentation. It was very interesting. I'm working with the same issues, you know, but at low scale, in fact, in my lab.
Okay.
But it's very interesting to know how you do that with more closer to the to some industrial aspect and some subsidies. It's very interesting.
Yeah, it's how to put this. You have to make it technically possible, but if it's economically not possible, it's not going to happen. I think there's only these days. I think at least in our country, you only get a subsidy if people have the idea that in the future it can work without the subsidy. So if you just need it for a certain time to overcome a development stage, but in the end, they hope that the whole technology can survive without the subsidy. That is a bit the Dutch situation that I think is probably different in France. But I could not take all the different situations in all the different countries also into account.
It's not the same law, the same head. But I'm completely agree with you. I'm not here to do only research or for articles, but for some reality.
Yeah.
Thank you again.
Welcome. We cannot hear you, Celine. Your microphone is...
Is it okay for all of you?
Yes, it is.
Yes. So, thank you very much, Finn. If there are no question, we can stop the record and see you back. And if there are other questions after this online meeting, you can ask them to me, and I will see with Ryan.
Okay. Yeah, just send them by email, and then I'll answer if I can.
And can you send us the presentation, please?
Yeah, I can send it to Celine, and then she can send it to you.
Yeah, thank you.
Thank you very much.
Yeah,
Ryan.
Welcome. Okay, have a nice afternoon.
Bye. Thank you.
Bye-bye.
Thank you.
Bye. Thank you.
Thank you. Bye.